using vector spaces, representations, and matrix multiplication, we've been able to rephrase our original problem in this class, solving a system of linear equations, as solving a single equation that involves a matrix, which is the matrix of coefficients, a vector of unknowns, or a single unknown vector, which, right, its entries are the original unknowns, and then on the right-hand side, a single vector. So this sort of rephrases what this kind of system is asking. Really, it's asking, right, A is acting like a linear transformation, and so we're asking what inputs to this linear transformation produce the vector B as an output. But remember how we originally solved this kind of system was we did row reduction. But what exactly does row reduction mean over on the in the matrix vector picture? How is it that row reduction appears? How could we sort of fit row reduction into this structure of matrices and matrix multiplication and vectors? Well, we can fit row reduction into this matrix vector picture if we could somehow describe row operations as actually being multiplication by a matrix. So if we have a matrix, let's say R, that does a row operation, right, then if we have a system of equations, right, that originally we would write like this, but instead we can write using matrices and vectors like this. How could we do this row operation? Well, if multiplying on the left does this row operation, then what we can do is just take this equation and multiply it on the left on both sides by the matrix R. And that will somehow make the row operation happen on both sides, right? It will do the row operation to the coefficients because we have our R times A here, and it will do the row operation to the right-hand side because we have R times B right here. So to make row reduction fit into this matrix and vector picture, all we need to do is figure out what matrices make these row operations happen when you multiply on the left by these matrices. So let's figure that out. And there's sort of a general principle in play, which is this. So if we have some row operation that we want to do, say that we'll assume that there is a matrix that does it. So let's say R does, like we were assuming before, let's say multiplication on the left by R does some row operation that we're interested in. How could we figure out what this matrix is? Well, if we're assuming it exists, we can actually use this matrix in a calculation, even though we don't know what it is yet. In particular, what we can do is multiply. So if this row operation, it will turn out that this has to be square. So let's say it's n by n. It has to be square because, right, if we're thinking about multiplying this by both sides of an equation like this by one of these matrices that does a row operation, well, on the left here, this matrix product is going to be m by 1, and this vector is m by 1. And when you do a row operation, that doesn't change the number of equations that you have. And so after we multiply by r, it should still be, this whole product should be m by 1, but that means that r itself has to be square. It has to be m by n, just so that the dimensions, the size of the matrices works out. Okay, so we know this has to be square, but how can we figure out what it is? Well, imagine multiplying this matrix, which again we don't know yet, by an identity matrix of size n. Okay? Now, there are two ways we can think about what this product would be. On the one hand, since multiplying on the left by r does the row operation, r times the identity matrix of size n is just the row operation applied to the identity matrix. Because that's what we said r does. Multiplying on the left by r does the row operation, so r times the identity is the row operation applied to the identity. On the other hand, any matrix times the identity matrix of an appropriate size just gives you the same matrix back. So this equation tells us what R has to be to figure out a row operation that does, to figure out a matrix that does a row operation when you multiply on the left by that matrix. All we have to do is do that row operation to the identity matrix, and then we'll have the appropriate matrix. So let's do that for our three kinds of row operations. So one of them was interchanging rows. So remember, to find the appropriate matrix, we just do this row operation to the identity matrix. So if we have an identity matrix of appropriate size, let's just interchange row I and row j. That gives us something that looks a lot like the identity matrix. It will have ones down most of the diagonals, but if we switch row I and row j, there's going to be, so it's mostly ones down the diagonal. But in row I, instead of there being a 1 in column I, it's in column j because we switched row I and j. So the 1 that used to be in row j, position j, has moved up to row I. So there's a 1 here and a 0 there. And then down in row j, the roles are reversed, and there's a 1 here and a 0 there. And everywhere except these two spots, it's 1s down the diagonal. So this is a matrix that does this row interchange. This is actually a special case of what's called a permutation matrix. And a permutation matrix is just the identity matrix, but with the rows rearranged in any way. And what permutation matrices do is, when you multiply on the left, the permutation matrix changes the rows of, so if we do any permutation matrix times A, this permutation matrix is just the identity, but with some rows switched around. This product is A, but with those same rows switched around. And in fact, if you multiply on the right by a permutation matrix, a permutation matrix, it's the identity with the rows switched around, but you could also describe it as the identity matrix with some columns switched around. And it turns out A times a permutation matrix on the right is A, but with the same column interchanging happening. So this is just two rows switched, so this is a special case of a permutation matrix. Okay, so the next row operation, next elementary row operation, is multiplying a row by a scalar. So to figure out the corresponding matrix that does this row operation, we should do this row operation to the identity. So let's multiply row I by C. And of course what that does is, most of the entries are still 1 down the diagonal. Off the diagonal everything is 0, of course. And then in the ith row and the ith column, multiplying, doing this row operation to the identity, it only changes the 1 in this position, and it changes it to C. So this matrix, multiplying on the left by this matrix, does a row scaling, and then adding a multiple of one row to another. So again, we'll start with an identity matrix, do this row operation, adding C times row j to row I. So what is that going to do? Of course, in most, or down the diagonal, it's actually all still 1s down the diagonal. So in particular, in the ith row, ith column, there is still a 1. Okay, but in the, so there's some jth, in the jth row and jth column, there's a 1, and we're adding a multiple of that up to the ith row. So in the jth position here, or in the jth column, in the ith row, there is something that is coming from the jth row, but it's 1, but it's being multiplied by C, so there's a C right here. And it's still 1 down the diagonal. So the matrix that does this adding a multiple of a row to another row is just the identity matrix, but then there's this constant in whatever position it is, depending on what row you're going to and coming from. So these three row operations, we can make them all happen just by multiplying by these very simple matrices. This one, and this one. These matrices, so these are the elementary row operations. So these simple matrices that make the elementary row operations happen are called elementary matrices. And what we'll see is, because multiplying on the left by elementary matrices lets us do row operations in sort of an organized matrix-oriented way, we can rephrase some operations, some sort of ad hoc operations that we used to do with rows in terms of matrices, which will give us nice ways to calculate things about matrices.